Alright, time for another draftphysics.com video presentation. Debate physics also, but no real participants. Real in like making a counter argument to anything actually stated or argued. So anyway, I thought I would just go over a possible way of clarifying, proving the argument. So I might as well illustrate the argument first. Okay. So I'm arguing that gravity is a time-dependent force, that it basically comes down in units, okay, that are a certain number of them, 5 per a certain number of times, seconds. So be 5 units of energy per second, 9.8 meters would really calculate out to a certain number of interactions with the gravitational force. And basically it's a depending on your mass is going to decide how much you collect, so you'll collect an amount proportional to your mass. And so it could be analogized to like rain, and you're just saying how wet do you get, or it could be analogized to the sun, and you're just saying the longer you're in the sun, the more suntan you get. It's that kind of obvious. So in a circumstance where you're trying to, say, launch a rocket into space, you could launch your rocket at 4.9 meters per second at a constant speed, right? So I just get it up to 4.9 meters right, of motion, and I just let it do that. Or it could be 9.8. I'm just saying it doesn't really matter. You get it going that much faster than the gravitational force pushing down. So as soon as you start moving, you're already defeating the 9.8 thing. Right? Kind of have to be. Yeah, so it's kind of built in. The counterforce is built in. So what you're going to see is 4.9 plus the 9.8 you're resisting. But anyway, or you could launch it to, really fast as you can get it up to a speed. You can just get it up to thousands of miles an hour as fast as you can. And so one circumstance you get into space in, 2 minutes, let's say, and in the other case it would take you, 3 hours and 43 minutes. And the fact is you'll use 1,000,000 times, something like that. Something like 1,000,000 times more fuel to do it this way than this way. So obviously NASA lifts rockets and gets them going very fast on purpose to get out of the gravity, to get through it as quickly as possible, because it's a terrible detriment to their progress. And even though it causes more air resistance, it's worth it, because the advantage of getting up here, okay, before the gravity consumes all your energy is really important. So it's time. All right, so I've also illustrated that by pointing out that if you were to lift something and you lifted it very slowly, or we could use the staircase example, if you were to lift something up a staircase, you never go a higher speed. So you're just doing this over and over and over again. So it's the same thing as lifting 1 unit of distance. So if this took 1 second, and each one of these things, once one of these lifts takes 1 second, you end up being in the gravity 4 seconds here, where if you launch it at twice the velocity, you'll get to the same altitude, okay, in just 2 seconds. So you're only fighting 2 units of gravity. So if you launch it at 19.6, and instead of doing this 9.8, 9.8, 9.8, 9.8, you will save energy. You'll only use half as much energy. And the same is true for going down, and that's the part that we really want to get to. So that's what we'll do now. All right. So to me, it's obvious it's a time-dependent force. And so the idea would be is to create an experiment. Now, I'll do it with a pendulum first, but no, let's just stay away from pendulums. But you have to do this. You have to do this very precise measuring to get the heights right. So, why do it if we don't have to? So let's just do maybe this idea, which I find appealing if possible. So you have a tube, and you're just going to drop a ball bearing. So let's just say you had the ball bearing here, and you have a little tiny pinhole, and you stick a little pin in there to hold it, and then you can pull the pin out. Okay, so there's a little pin release. And so you have, 4 units of height. and then you have 1 unit of height. Okay, so you have a pinhole there for 1 unit of height, pinhole for 4 units of height. And the idea would be is that you're going to place this, clamp it or whatever, okay, hold this device above a little nail, let's say, a nice hitting surface, and the nail is into a piece of clay, let's say. So the clay is inside, so you got a nice little clump of clay. And it doesn't matter, the clay doesn't have to be perfect, doesn't have to be in the container, really, I don't think. But regardless, we're just going to see how well the nail penetrates the clay. So I guess ideally it would be best to make it as symmetrical as possible for both experiments. So to have it in some sort of container would be ideal, I suppose. And just have it already in the clay a little tiny bit, the same height for both experiments. So you're going to do the experiment first from 4 times the height, and then you're going to do the experiment, and that'll give you twice the velocity. And then do the experiment, okay, from 1 height 4 times, okay. So the simple thing is that these 4, okay, is the staircase, okay. So you're basically going to prove the argument that it's not about time when it is about time will be proven, because you have the same nail here. You're going to hit it 4 times. Okay, and the argument is that the 4 times is definitely going deeper into the clay because it's 4 units of gravity. It's 4 9.8s. This is only 2 9.8s. This is 4 seconds of total free fall. This is only 2 seconds of total free fall. So this will be half the depth into the clay. Now, I guess I should draw that this way. Yeah, that'll work. So this will go twice as deep as this will, because it's 4 times it's twice the energy. So it seems a pretty good experiment. I don't see too much that can go wrong here, and that should settle it. That this is only twice the energy. This is only twice. It is twice as much energy. Okay, 4 9.8s is more than 2 9.8s. And that's all this has. It has 1 here and 1 here. 1 second worth here, 1 second worth here. This one will have 4 seconds worth. So I think that's simple enough. So I should be able to actually find these materials. I just have to find a tube. It'd be nice if it was clear, but I don't think I can find a clear one. This thing, maybe I could cut a slit in it or something. Anyway, it really would matter as long as the hole is in the right place where the pin holding it, and it should be just fine. And so it should be doable to make some sort of secure mechanism and have the ball just fall and hit the nail. And that should, there's always vagaries. You don't know exactly how clay behaves to velocity. So, I don't have any proof that faster things don't go through clay easier, but you don't know until you do it, I guess, for sure. So anyway, just throwing that out there. And so I'll try to conceive of other better experiments. But yes, we need a better experiment. And so I'll say again, for the sake of the argument, just so it's clear, Joule is made famous because he went to great lengths to create an experimental device that could do this measuring energy thing. But the great flaw in Joule's experiments is most of them involve dropping things off a pulley, a weight in gravity. And it was his assumption that gravity is a distant force, not a time force. So therefore, he thought dropping it slowly was the same as dropping it quickly. Where I'm obviously arguing if it's dropping slower, it's collecting more energy. It's real work. So when you lift weights, and you lift the weight slowly, you're doing more work than if you lift the weight quickly. Just a fact. And if you don't have that understanding, you're not going to be able to do lifting experiments and draw proper conclusions. All right, so that's probably enough. Maybe I'll just pause and see if I think of anything else. All right, well, I was thinking about it and really haven't come up with anything better. I was thinking of styrofoam or Maybe sand would be good, because then there wouldn't be any of this adhesion problem. You wouldn't have to worry about whether stuff sticks to the sides of it, and faster velocity, less sticking, some kind of crap like that. And I was thinking of layers of plastic film, but that's no good, because the faster you go, the easier it is to break. And like paper would be the same problem. So all of that doesn't get me anywhere either. So far, not thought of anything. So anyway, I'll think some more. Well, I guess I could point out something kind of obvious. This is this, just back to this joule argument, that it's more complicated than, you'd like it to be. It should be pretty simple, but you can't push a car, you can't do lots of other things because of this problem with how friction is applied to the thing you're measuring. So it would be best to have it do one thing, one unit of energy. So I was thinking of the scale thing again, and if you did put it on a scale, I think we already agree on what's going to happen. The scale is going to displace, a certain amount for 1 unit of weight. And it'll do that 4 times. So it'll displace a total, of 4 units. And obviously when you do this, I have it backwards, of course. All right, so you're doing the one distance over here. I don't have to change it really, don't have to change the drawing. All right, except to say this will be 2 pounds, right? So this will be twice the weight on this side, because it's falling twice the distance. And this will do 1 times the weight, so 1 pound, let's just say. It's going to read that on the scale 4 times. So it's kind of obvious that this will displace the scale a total of 4 times more. Twice as much distance. So the total here is just going to be the 2, because you're just doing this experiment once, so it would be 2 units of displacement. And this one will obviously have 4 units of displacement, demonstrating that it's more energy over here. It had pushed down on the spring more total distance. So I guess that's sort of a proof right there, because I think everybody's going to agree on what the outcome is going to be of that experiment. This isn't going to, this side is not going to weigh 4 pounds. So that's interesting. So maybe it's worth doing it with springs instead, and just, recording how much the spring displaces. Because the spring might be more consistent than the impediment driven into the clay. I'm just not sure about clay. Can't be trusted. But, it'd be worth doing it numerous ways, frankly. So, I guess we'll leave it there, and I'll see if I can think of some better experiment. There's got to be some way of teasing this out without building water tanks and, doing all of that hard work to convert the energy into pure heat and then measure how much heat it is. That does seem like a hard way of doing it. So I think I'll say that's enough of a video. I guess I could just add that one more from the beginning. So the simple question would be, why would they launch rockets fast if it's the same work if they go slow? So why would they try to get them up to as high a speed as possible to get, if it's the same amount of work either way? Yeah. That's it. I think it's kind of obvious. The answer is because it's not the same amount of work either way. It matters how fast you go. The faster you go, the less fuel you use. Fact. All right. Until the next time and such.